During the last video, dealing with moments of inertia, I talked a lot about beams and how the moment of inertia is applied to the bending of beams. And so today we're actually going to start looking at beams, looking at the internal forces inside of beams as well, because that is another thing that determines how much a beam's going to bend. Basically, the more force you put on it, the more likely it is to bend, but it also depends on the placement of those forces and a few other details. And so the way we're going to analyze beams is generally through diagrams called shear and bending moment diagrams. Those diagrams are going to tell us what the shear forces and bending moments are along each part of the beam. And this is actually very similar to what we saw way back on day 13 when we did method of sections. So difference here is that method of sections, we assumed all we had were tensile or compressive forces. So all my forces were purely axial, went in the same direction as the member itself. And of course, there's a few assumptions that we made for that to happen. Things like the forces only acting on joints. For beams, that's not the case. Beam, I have this big long beam and forces act all over the place. And so because of that, the forces are not going to be purely axial. There's going to be two other types of forces as well. And those are called the shear force and bending moment. And so that's what we're going to want to solve for both today and next class as well. So similar to what we saw for method of sections, premise of that is if my entire structure is in equilibrium, every part of it is in equilibrium. So I cut through my structure, replace it with some internal forces, and then I can solve for those internal forces based on one half of the structure. I'm going to do kind of the same thing for beams. I'm going to cut my beam at some location, get rid of one half of it. And in this case, instead of replacing that cut by one single force in the axial direction, I now have three forces. I have a force in the axial direction called N, a force in the transverse direction called V, that's my shear force, and a bending moment called M. So that force pushing down, not on a joint, is kind of causing two things. It's kind of pushing the beam down. It's also trying to make the beam bend. So that's why I have these two new forces, actually one new force, shear force, and also this one bending moment. And so now I have three internal forces or internal reactions. And these three internal reactions resist the external forces to make my object in equilibrium. And so as I mentioned, N, my axial force, acts in this case, horizontal direction. So again, when we're talking about beams, we generally talk about horizontal beams. So my axial force N is in the X direction. V is my shear force in the perpendicular or vertical direction. And M is my bending moment at that location. And just like I would do for the method of sections, when I cut this thing, I can put all my forces on there, or in this case, two forces in a moment at that cut. Depending on which side I keep, I have equal and opposite forces. So again, I always draw my normal force or axial force like I did in the method of sections coming out. So if I kept the left-hand side, N would be coming out to the right. If I kept the right-hand side, N would be coming out to the left. So again, equal and opposite forces there. V, I've drawn down for this top one, up for the bottom one. So again, equal and opposite bending moments, counterclockwise on the top one, clockwise on the bottom one. So again, when I kind of put these guys back together, all those internal forces cancel out. And again, like method of sections, it doesn't matter which half I keep. Either way will find me the same, or should find me the same answer. So I usually keep the easier side, usually. And just like we saw for, again, method of sections, I have these sign conventions. So I have the external force sign conventions. You know, X to the right is positive, to the left is negative, Y up is positive, down is negative. But then when I went to method of sections, I talked about internal forces, and the internal forces, because they act in both directions technically, there's different sign conventions. So for the axial forces, tension was positive, compression is negative. That's still the case here. But now I have these two new internal forces, the shear force and the bending moment, and there's sign conventions for those as well. So for the shear force, there's kind of two ways to describe it, so two ways to think about it. Both give you the same answer. One way is that the shear is positive if the portion of the beam on the left tends to be in the up position compared to that on the right. So in other words, the way these forces are acting is kind of tending to push the left-hand side up and the right-hand side down. The other way to think of that is that a positive shear force acts clockwise. So again, if the left-hand side is going up and the right-hand side is going down, that's a clockwise rotation. So that's the other way to think of it, which means obviously that a counterclockwise rotation is actually negative. So this is backwards than what we usually think of. We usually think of, moments are positive in the counterclockwise direction. Shear forces, positive shear forces actually produce clockwise rotation. So shear is kind of a weird one, and that's kind of the way I remember it, that shear is backwards. And then in terms of bending moments, definition for this guy, he's positive if the top fibers of the beam are in compression and the bottom are in tension. So essentially the top part's being pushed together, the bottom part's being pulled apart. So that makes it kind of bend upwards in kind of a smiley face manner. Again, the other way to think of that, which is equivalent, is that a positive bending moment will hold water. So again, if I've curved upwards, I pour some water in there, it's going to hold the water. On the other hand, negative is the complete opposite. So the top fibers will be in tension. So top fibers pulled apart, bottom pushed together, which will kind of tend to curve the beam downwards. Pour water in that, water runs off. That is a negative bending moment. So based on those sign conventions, if we go back to the previous slide, you'll actually see that every single one I drew was actually in the positive sense. So again, cut this guy. My normal force coming out, we all know that tension is positive, so coming out is positive. Same thing on the bottom, coming out is positive, so to the right on top, to left on the bottom. In terms of my shear force, this shear force V pushes down on the right, which kind of makes the left-hand side go up. So the left-hand side is up in relation to the right-hand side. So that is a positive shear force. Alternatively, this shear force is going to tend to rotate this object in the clockwise direction. Again, clockwise is positive. So again, that is kind of backwards. And same thing happens for the bottom one. This shear force over on the left here, pushing the left-hand side up. That means the left-hand side will be up relative to the right-hand side, or alternatively, that is also making this thing kind of want to tend to rotate in a clockwise manner. So again, either way you look at it, this shear force is positive. Then in terms of bending moment going in this counterclockwise manner up here is going to kind of want to pull these bottom members apart, push these top members together. So top in compression, bottom in tension. That is positive moment. Alternatively, it's going to kind of want to bend this guy upwards to hold water. And so that is a positive moment. Same thing with down here. If I have this moment going in that direction, that's going to push these top fibers together, going to pull these bottom fibers apart. So again, that is a positive bending moment. Pushing that up makes him want to, again, hold water in there, make a kind of smiley face. So positive axial shear and bending moments for each side of the cut. Instead of remembering those sign conventions as we did them, I kind of have a standard where I cut my beam. I usually keep the left-hand side. Obviously, I usually keep the easier one, but if it's kind of a 50-50 choice, I always keep the left-hand side. And then notice on the left-hand side, everything's normal in terms of to the right is positive, counterclockwise is positive, but then shear is backwards. So again, I think of it as shear is backwards and keep the left-hand side. And so in that case, normal or axial force to the right, shear is a backwards one. So instead of being up like it should be, it's backwards and it goes down. Bending moment is counterclockwise like it should be. And then if I keep the right-hand side, everything's just the opposite of what I would normally do. So that's actually the way I remember the sign conventions. One other alternative definition for the sign convention for the bending moment is actually a kind of nice one that I like. If you think of something that's going to hold water, or top side in compression, bottom side in tension, that makes kind of a smiley face. So smiley face, positive moment. So smiley face is positive because smiling is happy, positive. On the other hand, if something's going to shed water, it's kind of a frowny face. Frowny faces are negative. So yeah, negative moment for the frowny faces. That's another good way to remember at least that one. And so because we're dealing with beams, there's three kind of standard beams that we see a lot, and we have seen a few of these previously as well. There's a simply supported beam, so essentially a support at each end. So this is kind of drawn not completely to scale, but each of these is kind of right at the very end, so not much overhang on each side. So again, some support, pin or roller on one side, another support, pin or roller on the other side. That's a simply supported beam. There's an overhang or overhanging beam where one of these is kind of moved inwards, or even both of them could be moved inwards. I just drew it here where this roller was moved in, but again, it could be right side, could be left side, could be the pin, could be the roller, could be both. If there's some portion of the beam that's overhanging a significant amount, or both, that's an overhanging beam. And then we've also seen these cantilever beams stuck into the wall. So those are kind of the types of beams we'll be seeing. And then to analyze these beams, essentially what we're looking at is the load, shear, and moment diagrams. And so what we want to do is essentially determine those axial, shear, and bending moments inside the beam. So we want to know how much basically force there is inside our beam at any location, kind of the same way we did for the big structures when we dealt with method of joints and sections. I want to know how much force is in each member, because that's going to help tell me, what that member needs to be made out of, how strong it needs to be. Exact same thing here for the beam. I want to know these internal forces, so I know, again, how strong my beam needs to be. Another nice thing about these is it also tells you not only what those values are, so what the maximum shear force and bending moment is at any location. It also tells you where that is. And so in terms of where this thing might break along its length, that's helpful as well. So the standard diagrams are load, shear, and moment. There's actually a fourth one also, the axial. There's also an axial force diagram. It's not always drawn though, because a lot of times for these beams, there's just purely vertical forces. If there's no force in the x direction, your axial force is always 0. So a lot of times you don't draw that because it's just 0. So standard is to draw at least these three: load, shear, and moment. So the load diagram is essentially just the forces acting on the beam. Forces acting on the beam is just the free body diagram. So your load diagram is essentially just the free body diagram. So first thing you do is you take your beam, you have your supports, replace those with the proper reaction forces, solve for those. And once you've solved for those, put them on your free body diagram. And that is the entirety of your load diagram. So that's the easy one. Shear diagram, usually drawn right below that, is showing you the shear forces at every location along the beam. And then the moment diagram, usually drawn right below that, shows you the bending moments, again, at every location along the beam. And they are usually drawn in that order. So load on top, shear right below it, and moment right below that. One reason is because you can determine the shear diagram essentially comes from the load diagram, moment diagram comes from the shear diagram. So that's why you do that in that order. And so the way we're going to do it this class, so again, there's two ways we're going to do it. This class is kind of the way we described before. I'm going to take my beam, I'm going to cut it, I'm going to replace that cut with three unknown internal reactions: the axial force, the shear force, and the bending moment. And then throw away the other side, do rigid body equilibrium with those three unknowns. So solve for my three unknown internal reactions. And that gives me values for those forces at that location, and then cut it as many times as I need to make nice smooth curves for my entire length of my beam. And so that's how I'm going to draw these diagrams this class. And so here's a few simple examples. I have a cantilever beam, just one single force. And generally when I make my cuts, I usually have to make cuts kind of where things change. So if anything changes, if a new force comes along, I'll have to make a new cut. This one's fairly simple, only have one force and my reaction forces. So just have to make some cut somewhere between those two. So anywhere between A and B. Easiest thing to do is call that some distance x, because if I call that some distance x, I'll get a function of x. And so that way this basically covers the entire length of my beam from 0 to L at any x location. It's better than cutting it at, say, 1 meter, then 2 meters, and 3 meters, and having to plot all those points. I just plot it as a function of x, which is what these are. And so what I do when I get that, obviously, is throw away one side, draw my normal force, which in this case is going to be 0, so don't have any axial force diagram, because again, there's no x force here. So that one I actually don't really need. But I do have a shear force. Again, keep the left-hand side. So left-hand side shear force goes down. And I have a bending moment, again, positive direction, counterclockwise. And then I'll get V as a function of x. What I'll find in this case is that it's just a constant equal to negative P. And then I'll find my bending moment for this half. And I'll find that it's a linear function, starts off at 0, ends up at negative PL. So those are my shear and bending moments for that one. The second one, a bit more complicated, have an overhang beam. Again, some reaction forces, AY and BY. In this case, there's kind of two things that are happening. I have this force, then I run into these reaction forces, so I want to make one cut there. And then I have this new distributed load going on, so that's something new. I'll have to make another cut here. But this case, only two cuts. And again, do the same thing. I have technically some normal force or axial force, some shear force, and some bending moment. So I'm going to do it once for this guy. And I'll find, again, similar functions to what I have over here, a constant value for the shear force, and then this kind of looks a bit curved, but that actually should be a straight line. I don't know why it looks a little curved. Again, similar over there, linear function for my bending moment, and then do it over here, do it again, so new cut. Again, I'd either keep the left side or right side. I'll keep the other side this time, so axial force, shear force, bending moment, and in this case, I'll find a linear function and a curve for my bending moment. So class today, we'll go through a lot more examples and actually do that in detail and actually see where these functions come from and where the diagrams come from.